Okay, thank you. First of all, I would like to thank the workshop organizers for inviting me. And the topic of my talk today is solving math problems by joint parsing and cognitive reasoning. My name is Song-Chun, and I'm currently with the Beijing Institute for General Artificial Intelligence, and also jointly with Peking University and the Tsinghua University. This is a joint work with mainly four people. Yiling Hong, she is a PhD student at UCLA, and Changsong Liu, who is a research scientist at the Beijing Institute for General AI, and Han Lu and Qi Zhang, both are PhD students at UCLA. This work is motivated by, for example, this is a fifth grade science text. So basically, the title is you show two images. One obviously is a summer with a pond with two dogs swimming in a pond and trees. And the next one obviously looks like it's winter, someone skating on this lake or pond. The question is, which of the following has caused the changes in the pond from A to B? So this is a science question. But first of all, it has to solve a image parsing problem. First of all, we have to parse each of the scene over time, right? A and B into what we call a parse graph. Then you have a hierarchical organization. Then the parse graph give you a description, a semantic description of the scene. And then when you have two parse graph, and then some attributes changed, for example, the temperature, the winter, from summer to winter. Therefore, we represent those things by attributes of fluence. For example, the sky and the lake, and so on. So this is what do we call a cognitive reasoning? Means that what cause the causal change of the fluence or attributes in the scene. Let me give you a typical example. What I mean by parsing. So suppose you give a picture like this, a person. A person, first of all, you parse it by a so-called phrase structure grammar. So the parse graph is a decomposition of a person go to body parts, and the body parts further go to little elements and go to the grounded on the images. This is so-called phrase structure grammar. And then you have so-called adjacency grammar, which is showing the articulation and the connections of the body parts. For example, show the green line here. So you have this pose estimation. But then at each level of the parse graph, you have a number of attributes. For example, the whole body, you have a gender, age, and also the other body also have gender, age, length, color, type, and the head, and so on. So therefore, you have different levels of attributes over time, over the different levels of concept. So over time, when this person moves, as we see from winter to summer, summer to winter, or this person moves, some of this attribute will change. So we have appearance attributes and geometric attributes. Of course, these attributes will also associated with probability. So the attribute will change is caused by certain action. The action in the previous example is a physical temperature change. Here is somebody has an action. So this is the representation that we use for parse a picture. Similarly, if you want to parse a picture like this, the tree and the dog and so on, the motion. So then in a more complex scenario, the parse graph includes what we call a joint parsing. That means, for example, this picture, you go from 2D into a 3D, and then you also have time. You try to represent it by temporal change before and after. What this person was doing before and what she will do after. And then you also do some cognitive reasoning. The cognitive reasoning means that the physical attributes behind. For example, you will reason the water in this kettle was must be hot, and the cup is empty, and so on. And then you have some other reasoning, like a social reasoning, like a mind, the belief, and the intent, and so on. All of these are summarized in what we call a spatial, temporal, and a causal NL graph. So the path graph is a specific instance. The NL graph summarizes everything into a grammatical model. Okay, so let me give you a couple slides to illustrate what I mean by NL graph. An NL graph basically is a graphic probabilistic representation for some logic formulas. For example, you have a production rule A equal to AB or ADC. So what you do is like all nodes. This here is all, and then A could be A1, A2, or terminated into a terminal nodes, which is square, or can be further decomposed into a path. And then the path tree will be augmented by relations, spatial relations, temporal relations, or physical relations. Say someone support the other object, so on. And then you have this attributes, which is the property or feature or property, geometric color or appearance features or topological features associated with each of these nodes. So this is the attributed spatial, temporal, and path graph. So suppose give you an example. This is a NL graph. And then when we select all nodes, for example, all nodes from A, B have two choices. You go this way. The C has three choices. You go this way. Then this red lines will generate a path graph. And then you can generate a so-called configuration because the path graph is hidden, latent structure. What you observed is the terminal nodes with a certain configuration. That's called a configuration. Then you have a multiple path graph can be generated from this NL graph, and then you have different configurations. So we are going to use this representation to solve a sequence of mathematical problems, including today I would present three typical examples. One is the IQ test. Second one is math word problem and the geometric theorem proving problems. As you may know, most of this kind of math, algebra, or geometry problems are abstractions of some real-world scenarios. So therefore, whatever we try to represent the real world, they are simplified and abstracted into their representation. So therefore, the spatial, temporal, and the causal path graph, NL graph, will still be used for solving these problems. I will show you how. So IQ test is a typical abstraction of what we call a video understanding problem. For example, this is a so-called Riven's progressive matrices, RPM. You're given 8 pieces at 3 rows, and then you try to fill in the remaining one. The choice is 1, 2, 3, 4 to 8. And so you want to know which one fits most, right? And how do we formulate this problem? Okay, the problem is that each row is like a keyframe of a video. Something is showing moving going on with some temporal or causal changes, and then you have 2 examples to show you, like 2 sequence of examples. And from those 2 examples, you want to learn a model, and then you fit into the third model, and then the best fit will be, for example, in this case, number 6. So this basically is a video parsing and online learning adaptation, as well as inference problem with only one examples. The second type of question is a math word problem. For example, this is a typical elementary school math. A truck travels 100 kilometers in 2 hours. At this speed, if it travels for another 3.5 hours, how many kilometers will it complete for the entire journey? So the answer is 275. So the solution obviously is a path graph, right? And the path graph is expression, algebra. Then you have terminal nodes, which are those numbers, key numbers, and the numbers will be associated as the attributes like speed, distance, and so on. So you solve the problem as a attribute propagation problem. Okay, and this is cognitive reasoning, what we call it. And this is another type of question that my student generated. It's called a icon QA. It's basically ask you which object is to the one, is next to the one shaped like a cube. So the answer, and the cube is here, and then this is the watermelon. So you need to first parse the thing, and then you know the spatial relation, and then you know the attributes. Which one is a food, for example? What is a sphere? What is a cube? What is a cylinder? Right? Those are the attributes associated with each of the nodes, and then the nodes are part of the path graph with spatial relations. So by reasoning in this path graph, attributed path graph, we can answer those questions. The third one is a geometric proving problem. Like you're given a diagram, you have some text description, and then you try to answer the question. Usually the question is give you certain part of the attributes for certain part of the path graph, and then you propagate the attributes to some other part. The attributes including the length, the angle, and the area, the size, the volume, and so on. Okay, so all those problems, the characteristic of these problems is that there's multimodality, means that they contain some diagram, some natural language description, and pictures, and then we can use a unified framework in the sense that we doing this problem parsing. Joint parsing means parsing the diagram, the visual part, and the text part, natural language understanding. Both of them generate a path graph. We call it joint parsing. And then you're doing some reasoning by propagating the attributes in that path graph. And then this involves some cognitive reasoning, multiple human reasoning skills, like spatial relations and attributes, semantics, and so on. Okay, so let me go through these three examples in a little bit more details. The first one is an IQ test in the Inference dataset we collected by Pine Liu and Stephen Gong, some other students in the lab. So what do you have in this test? Like a matrix, right? Each of these elements, as you can see, is a decomposition of, say, okay, the whole matrix, including 3 rows, and each row included by a decomposition of certain inside-outside relation or parallel relations or certain layout. So the layout, you have different types, usually. Say you have a center relation called center, and a 2x2 grid or 3x3 grid, and then you put objects in and or on and off. So they have some attributes like geometry and shape, like the rotation, orientation. They also have attributes like color or appearance, texture, inside, empty or filled, so on. And the relations between them. So you have a number of such relations and a decomposition. From there, you generate many of this kind of test. So this is a very interesting problem because it can defeat deep learning neural network type, because in this case, usually you only have one example, and on the fly, you select example, you're going to figure out what concept it is. So what I mean by concept, I will show you in a moment. So in this case, for example, you have the first row. Let me say I will generate a path graph. Okay, this attributed path graph. Say this has one object with certain attributes to it. And then you generate another path graph for this guy and this one. And then you figure out that this is a temporal path graph. So because each row is like a movie with 3 keyframes. And then between them, you generate a so-called temporal path graph. So what has been changed? What are the action goes from 1 to 2, and then from filled to empty. For example, you have some actions. That is the T energy. And then you look at the second one, and then it also is using the same movie, but it's different clip, right? And then you have another path graph. Okay, this is spatial and temporal path graph, and sometimes you have a causal, means that a certain action happened. And then you try to use that same path graph or model to apply to the third one. For example, the correct answer is this guy. It fit to that model, okay, and then the other one does not fit or fit and not as good as the number 4. So this is the process that we are optimize this path graph at the same time on the fly to learn what is the concept, and then you find the correct one fitted with the other two, and then you have a coherent representation. So suppose we represent this problem is as a posed as finding the underlying concept of this problem. So each Reven's test basically defines a concept. A concept is a set. Usually we call concept as a set. The set is a set of TPG, temporal path graph, which is an event. Each row is an event. So you have 3 little events. The TPG, which is the third row, and then you have TPG of the first row and the second row, TPG. So you have 3 events, which is abstraction of what you observed, the hidden underlying event, the temporal path graph. And then you project this 3 path graph. Okay, the H is a projection. Basically, you select certain elements of the TPG, so you project it into a new space, which is a vector H0. So then you realize that all the 3 components share the same vector. So that is what we call the concept. This is coming. This kind of concept comes from what we define a pattern, like a texture or something in computer vision. That means all texture, they are equivalent because they have the same statistics. Here is that all the 3 rows share the same type of projected features or statistics or structures in here. So, but the interesting thing is that this TPG needs to be inferred. They are latent. So that means you are in a loop trying to figure out what's the TPG, at the same time try to figure out what is this projection and what is the maximum common H0 that defines this concept. Okay, so the full problem is like we on the fly adaptation means that we need to infer the SPG for total 16, right? You have 8 observed and then 8 answered. So total is 16 path graph. You infer it. And then based on the 16 path graph, you infer the temporal path graph, TPG1, TPG2, and the TPG3. 3 has 8 possible path graphs. And then you fit all those guys into a representation and see who has the most coherent representation after you do the projection. Okay, that's the whole process. I don't want to go to details, but this one actually, I'm still asking the students to formulate it in a simpler way. Okay. Now, given this TPG, you have this generative process, as we see. You can use that for inference, but also you can use it for generalization. So basically, you have the condition, then you can predict what the best choice it is. So applying this algorithm, the result, numerical result, this one is largely, I don't have that slide here. So on that driven test data set, it's overwhelmingly, better or outperformed traditional neural network type of deep learning. As you can see that because the major problem is of deep learning or neural network is the lack of explicit representation here. So the second example, we apply the same framework into math work. For example, this is a math work problem. Currently, there are many other methods like neural network plus deep learning that construct embeddings and then encoding, decoding, and then try to solve this problem. The major problem is, as people already noticed, is the lack of generalization capabilities. And this neural network solvers can fail in scenarios that, for example, this is a problem that is solved correctly, because we realized that they can find a similar problem in a training set. But if you change it a little bit, then it can be confused. Or if you insert certain distracting numbers, it can also be just kind of distracted in a way, give you a wrong answer. So the fundamental reason is that it does not have a correct understanding, which means parsing. And then they solve the problem not by a analytic cognitive reasoning here. So what we do is similar to what psychologists try to do. They call this a situation model. A situation model is frequently used in psychology and cognitive science for solving this algebra story problems, in the sense that you have a car A and a B, and then they basically try to give you a situation. That situation in all case is basically spatial and temporal parsing. Okay, it's a pass, right? And then you pass it, and then you augment it with attributes like speed and so on. So I'll give you this example. A car travels from city A to B. It travels for 6 hours on the first day, and it spend at a speed of 65 kilometers an hour, and blah blah blah. So first of all, you generate some name entity, and then generate nodes, and then associate nodes with attributes. For example, city, and then you have 2 cities, and then you have distance between the cities. That's the attribute. And then the rate of a car, like speed, all right, and time, the travels. So you generate a simple path graph associated with all these attributes, and you try to figure out the relations. Those relations, sometimes you have some constraints. Okay, those comes as a theorem. Okay, like distance always equal to speed times time, for example, or the total price equal to the units you buy times the unit price, right? So we have a training process. Okay, this situation model is basically attributed grammar or path graph. So what this is a work by Yiling Hong. She did a training process in the sense that if you get something wrong, obviously the bottom-up proposed entity or relations could be wrong, and the constructed path graph therefore sometimes correctly answer the question, or sometimes cannot. So they're generating the failure buffer or success buffer. If successful, they go back to retrain, and then if it's failure, we needed to close the loop. This is a work done by another student, Qin Li. He tried to close the loop in the sense that using the failure example to redo some of this, the bottom-up process, okay, to correct the path graph until you generate the right answer. So the path graph will be generated by maximizing the joint cognitive reasoning plus this text parsing problem. Okay, the iterative learning process shown here is like trying to still try to train, fine-tuning some of this bottom-up process. Okay, well, I'm not against using neural network in the sense that if neural network can be used for detecting certain name entity or relations, I think that's fine. And then this path graph will propagate some of this. This is basically it's a 2-level representation. You have a path graph abstract, and then you have a neural network which is dense, and then you have to close the loop between them to do the training. So this is some tested result. The SMART is what she did that can give a much better results than the literature. So particularly for a test set that has out of distribution questions. Okay. Then they further extend this to some icon QA problems in some paper. So to answer questions that involve a diagram with visual and then causal. For example, this is the causality from the oven, right? The pizza from the ocean take out, and then what's the temperature. And so this is some common sense reasoning problems here involved. It's quite interesting to do this kind of joint parsing and cognitive reasoning. Okay, this is some more examples of layered data sets. Looks like I'm running out of time. And the third one quickly is the geometric problems that we are solving by this geometric 3K, so 3000 geometric multiple choice. Also, by parsing the diagram, you generate some what kind of formal language which is augmented, like an area, those attributes, sum-learned attributes, sum-learned relations. So those attributes and relations were augmented into a path graph. And then the path graph will propagate the attributes. This is an example. For example, you have this diagram decomposed triangle ABC into two triangles, ABD and BCD, ABD, BCD. And each of them have attributes, sum-learned angle. The size of the angle are equal. For example, this is 32, this is 54, this is 90. So you have some thing assigned, and then use some theorem. For example, the sum of interior angles is 180 degrees of a triangle. Then you can propagate this attributes go up and down. And then, for example, this line AB will equal to 32, and then this angle equal to 45. So this is how you propagate the attributes up and down in this path graph. And then you, based on that, you do the second level of parsing, and you keep parsing the, propagate the attributes, and then give you the final answer. So typically, this is the interpretable general geometric problem solver. Okay, this is what he does. Give you some 57%. But if the natural language, if the path graph is ground truth, he can give like 78 or 80%. The reason is not 100% because he does not have all the theorems inside this construction. Of course, people will ask where you get the theorems. Those theorems are coded by the attributes functions propagation in that NL graph. Okay, so for most of the problems were solved in 2 or 5 steps in this data set. We have another ambitious project by Song-Chun Liu. Basically, try to solve this problem. You have a diagram that goes to a path graph, and you have language goes to another path graph. You jointly generate a joint path graph. But some of the problems need auxiliary lines, causal reasoning. That means that I need to add a new line to decompose, for example, or even 3D, fold the coin into a coin, fold this fan-shaped area into a coin, and so on. So this is auxiliary construction in 2D or 3D will furtherly generate a new path graph, and from there you solve the problem. This is some tricks of the path graph and the auxiliary lines. This is finite space. Okay, different type of path graph, then you can solve it differently. Okay, I'm running out of time. I want to thank you, and also thank my students who are working on this problem. Okay, thank you. Bye-bye.